Thanks a lot. Thanks a lot for the introduction. And welcome to the last day of this summer school. So what you will hear now is pretty much the work I've done in the last few years during my PhD, okay? And what we have done in this European project. And the title of my presentation is called Self-Organization in Distributed Visual Sensor Networks. So when we think about visual sensor networks, we usually think about something like camera networks, right? And especially in the UK or in London, you might have seen something like this here, right? So you might have seen these surveillance cameras, CCTV cameras. Because according to a study in 2002, there are around 4.2 million of these cameras in the UK. People have doubted this figure, and by now it's also about 13 years old. And there is a more recent number from the British Security Industry Association, right? And they claim there are between 4 and 5.9 million cameras in the UK, and this is from 2013. So the number is probably quite right. If we think about security cameras, we also often think about something like this, right? People sitting in rooms with a lot of monitors, analyzing video streams, right? There are a couple of things they would like to do. So, for example, they would like to monitor traffic. They would like to identify accidents or congestions on motorways. They are trying to prevent crimes with camera systems, right? Scare off pocket thieves. They would like to control crowds in case of disastrous situations or any public events. But they also use camera systems for production line surveillance to guarantee product quality, right? So it's not always just surveillance cameras for people, even though we are doing building monitoring and person tracking. But as I said, we often picture this as people sitting in rooms, getting all the information on their screens and then analyzing that themselves. I guess I don't have to talk about why this is a huge bottleneck, right? And that this has a lack of flexibility and robustness, right? So I don't want to talk about this so-called dumb cameras, right? So instead of using these dumb cameras that are quite popular nowadays, we want to combine the image sensor with a processing unit and a communication interface. And when we combine them, this gives us this sweet spot. This is where the smart camera resides, right? So the smart camera is, simply speaking, a combination of an image sensor capable of processing the image on site and then transferring only aggregated data. All right? When we think about smart cameras, we are usually thinking of two different types. The general purpose one, which is built from a standard CPU or computational device like a Panda board or a Raspberry Pi, combined with a simple image sensor, for example, a webcam. Right? There are also special purpose smart cameras, like the one I've pictured here, that has been built in Klagenfurt with the purpose of protecting your privacy. Right? The nice thing is, again, the image is captured at the device and does never leave the camera per se. Right? And that's what we can do with the smart cameras. We can use them to process images on site. We don't have to transfer it to a central control. Okay, so what can we do with smart cameras? Right? For example, we could allow them to calibrate themselves. Right? This would mean that we can identify their location and their orientation within a 3D space. We can do event detection. Did somebody enter a certain area within the field of view? We can do object tracking. This means follow an object through the image. I will talk about this in a few minutes. And we can do view selection. So in a network of cameras, we can allow our cameras to decide themselves which one is the best view. We can enable our network to optimize coverage. We can even do 3D reconstruction, either of objects, but also from an entire scene with a network of cameras. And we can do some information fusion and consensus finding to improve the quality. Right? And finally, we can do some task assignments and coordination. But I would like to talk about self-organizing stuff we can do in distributed smart cameras. Right? So what I'm going to talk about today is distributed visual tracking, which is a special case of visual tracking. Then I will talk a little bit about topology estimation. How can we define our neighborhood? I will talk about the flexibility and the robustness of our approaches. I will talk about how we can enable our cameras to select the best strategy and the best behavior within the network of cameras. And I will also talk about coverage and redundancy management of a camera network. So the cameras we have seen, or the camera we have seen earlier, is an embedded device, right? And pretty much all our smart cameras are embedded device. We don't have a full-fledged PC or even framework server in the background. Okay? So there is quite a large drawback when it comes to resources, because they are quite limited, right? We have limited bandwidth, we have limited processing capabilities, limited memory. If we have a completely wireless device, we even have limited battery power. Okay? So how can we overcome these limitations? Well, I said this before a couple times, but we can simply put a couple cameras together and let them operate in a network. Right? This allows us to distribute tasks and distribute load among multiple cameras. Okay, let's get to tracking in a single camera. I know a couple of you are working with tracking algorithms. I don't know if all of you do, but just a very simple explanation, a very baseline explanation. In tracking, in visual tracking, what we do is we tell the camera that we want to track a specific object. So let's say we want to track this chap in the blue shirt. This basically tells the tracking algorithm what he should be looking for in the consecutive frames. Right? And then in consecutive frames, the tracking algorithm tries to identify and detect the same features again in consecutive frames. So this is quite fine. Let's do this in a network. Let's assume we have here a camera network with 4 different cameras, C1 to C4, and their corresponding fields of view. The cameras then try to track this yellow round object. Okay? This is all quite fine and quite nice, works quite easy. The 3 cameras seeing the object, track the object. This is indicated by this purple square here. Right? So this is fine. There is no need for coordination. Right? But a problem arises if we have multiple objects. Because in that case, tracking multiple objects per every single camera might not be feasible or even possible, okay, due to their limited resources. So trying to track all visible objects in each available camera might waste quite valuable resources. Okay? As an alternative, we proposed distributed tracking. So this means each object is only tracked by a single camera. Right? So with our simple examples from the beginning, C3 and C4 are not tracking anymore. It's only C2. Well, the big problem here is when the object is about to leave the field of view and we don't have a central controller, we have to somehow decide who should continue tracking. Which camera should take over the tracking responsibility? Okay? And if we don't have a central controller or a person defining this in the beginning of our network, at the setup of our network, we have to find a self-organized approach, right? And that's why I'm talking about self-organization. So far, what do we have? We have a set of cameras, C1 to Cn. We have a set of objects who can be tracked, O1 to OM. We have cameras who are able to autonomously track an object within their own field of view. But also, we have a communication interface. So we enabled our cameras to communicate with other cameras in the network via message passing. Then we have implemented a utility. So we allow cameras to generate some artificial utility by tracking objects, right? And we implemented our cameras that way that they try to maximize this utility. So their goal is to track as many objects for as long as possible to achieve as much utility as possible. All right? The most important thing for distributed tracking is that two cameras can never track the same object. So we defined a set for each individual camera called OI. This is the set of owned objects. And two cameras' owned objects may never contain the same object. And then I will also talk about behavioral strategies, and we'll present in the course of this presentation 6 different strategies. So our goal now is to coordinate tracking responsibilities within the network, right? But we don't only want to do that, we also want to keep the best view of the object, okay? So we want to always tell as accurately as possible where the object is. And I said we have different strategies. So we also want to have the optimal strategy for each camera to not waste resources within the network. But we want to do all this without any a priori knowledge, right? So we don't want to give the network of cameras any information about its neighborhoods. We don't want to give it any information about the scene, the objects, the movement of the objects, or anything. Okay? We just deploy the cameras and we want them to organize themselves. There has been quite some effort to do this in the last few years. Unfortunately, the last line is not visible anymore. Well, I will tell you what's going on. The thing is that there has been a lot of effort doing this. But as you can see, most of them did not care about the best view. They were happy with just being able to track the object, right? So only in recent years, Morioka, Lee and Banu and our approach tried to also include the best view on the object, right? The thing is, Morioka did quite some pre-processing, added a priori information, and also just used non-overlapping cameras. So their cameras always overlapped, okay? In contrast, Lee and Banu did not use overlapping cameras, but they transferred all the images to a central server, who then decided which camera should continue tracking. So this is a bit of it, yeah. Well, we did it in a completely distributed way. How did we do this? We were inspired by virtual markets, or by markets in general. So we treat our cameras as buyers and sellers on a virtual market. And the commodity they were trading are their tracking responsibilities. And we did that by using auctions. Okay? So let's take our 4-camera example again, so you get an idea how it works. So C2 is tracking the object within its own field of view, and that's fine, right? But at some point, the camera may decide that it wants to hand over the tracking responsibility. So what it does, it initiates an auction. And this auction contains a description of the object to be sold and a request to other cameras if they would like to take it over. Okay? So other cameras will then try to identify the objects within their own field of view and value this object. So basically defining how much they might gain utility by tracking it. So they return a bid containing this valuation to the auctioneer, and the auctioneer then decides which camera should get the tracking responsibility, and then transfers this tracking responsibility. We use so-called victory auctions for that. Victory auctions are single sealed bid auctions. So this means that each camera for each auction only has one single bid. It can only transmit one bid, and other cameras in the network do not know what other cameras have transmitted, right? Only the auctioneer knows what bids have been transmitted. And the object is then sold to the highest bidder, but for the second highest price, okay? So there's an exchange of utility between the cameras for being allowed to continue tracking, okay? Why the second highest price? Well, this results in a quite nice property in victory auctions because the most dominant strategies for a camera in the bidding process is to bid truthfully, okay? Not to overspend or underspend money. So we can do this, and the next camera can continue tracking. We can do this whole process completely distributed and without any a priori knowledge. Right? So we don't have to introduce any information a priori before we set up the camera network. For this approach, so if you want to know more about victory auctions, I can give you some literature. It's quite an interesting area of research. But I will not go into detail how it works, that the most dominant strategy is bidding truthfully. But in general, for the auction mechanism and the distributed tracking approach we designed, you might have two more questions. The first one is, when should we actually start advertising our objects? Right? And the second one is, which camera should be invited for our auction? Well, let's start with the first one. When should we advertise our objects? Well, there might be quite a plethora of approaches on how to do this. We came up with two very simple auction schedules. So the first one we called active, and the second one we called passive. The active approach tries to sell the object with a very high frequency. So basically constantly try to sell the object to another camera. This results in quite a lot of communication, right? We are constantly sending out invitations and also quite a lot of processing effort on the network-wide level, right? Because other cameras now have to try to find the object. But we always get the best result. Right? On the passive approach, we only initiate auctions when the object is about to leave the field of view. This results in much lower communication effort and processing effort, but may not always result in the optimal handover. Right? It might happen that another camera has seen the object better much earlier. So to the second question, which camera should receive an auction invitation? Well, all of them might work with a small example with just 4 cameras. But if we think of larger networks with 50 or hundreds of cameras, this might be infeasible. So only a few. But now the question arises, how can we select an appropriate subset from our set of cameras without having any a priori knowledge, right? So if we don't know who's our neighbor, well, we can learn who is our neighbor by exploiting the trading behavior. So by analyzing who we did trade earlier, we can learn our neighborhood. We were inspired to do this by the foraging process of ants. So ants, when they try to find food, they will look for pheromones, right? And if they find food, they will deposit pheromones. So what we did is we used artificial pheromones for each trade. So every time a camera sells an object to another camera, it will locally create a link between itself and the other camera. Very simple example, 2 cameras, we trade, I and X. So I creates a link, tau IX, right? So this link we call the vision graph. And this is just locally on every individual camera. It's not a network-wide representation, it's just a local representation of the local neighborhood. The foraging process in ants, what they also do is if they pick up a pheromone trail and find food again, they will again deposit pheromones. So this will make the pheromone trail stronger over time. We're doing a similar thing, right? So every time we sell the object again, we increase the link strength. Okay? With pheromones of ants, if the food source is depleted, the pheromone will evaporate. And we are doing the same thing. If there is no trading going on anymore, over time, the link will evaporate. Okay? This introduces a forgetting factor. So we unlearn information we have previously learned if it's not valid anymore. So this allows us to focus our marketing efforts and focus our advertisements when soliciting for auctions. So in addition to communicate with all cameras in the network, we came up with 2 more communication policies. The first one's called STEP, the second one's called SMOOTH. And they both rely on our learned vision graph. STEP communicates, or basically the probability to communicate with another camera in STEP is based on a certain threshold. So if a link is above a certain threshold, and the approach will communicate with the other camera. If it's below, then there is only a low probability to communicate with this camera. And in SMOOTH, the probability to communicate with another node is based on is based relative to the strongest link within the local vision graph. Okay? So this gives us 6 different strategies based on a combination of our communication policies and our auction schedules. So we have active broadcast, active step, active smooth, and we have passive broadcast, passive step, passive smooth. Right? So we tested these 6 strategies on the one hand in simulation with 26 different scenarios, 17 cameras in our simulation tool called CamSim. And we also built a simple real-world camera setup, camera network, with 13 different scenarios and 4 different layouts. And what we were looking for is the network-wide performance, right? And we measured, on the one hand, the utility throughout the entire network, as well as how many messages have been exchanged in the entire network. We did this over 30 runs, calculated the mean, and then normalized the outcomes by the highest number, okay? Just to have it on the same scales. This is one of our examples we tested with 16 cameras. Here the green dots represent a camera, and the triangle represents the field of view, the respective field of view. So what we found out with these 6 different strategies is that there is quite a strong trade-off between the communication effort and the utility we can generate, right? And we got similar results with pretty much all our scenarios. Also complicated ones with a lot of different cameras just randomly located. But we always got this quite nice tension, right? So this would allow an operator now to say, well, I have to save resources, for example, and select passive smooth. He still gets quite a good tracking performance, but needs much less communication, but also, respectively, processing power. All right. This is distributed visual tracking. But we also talked a little bit about topology estimation, right? So we just heard about how we can learn the topology within a network. So let's talk a bit about flexibility and robustness of this approach, right? How does it help us if we think about static camera networks, right? We might run into problems when we have dynamics. So let's assume we add a new camera. We set up our cameras, I just put down here 3, and in static networks, we would have to define the neighborhoods a priori, right? The thing is, if we add a new camera, so tracking would be fine in 3 cameras. If we add a new camera, this new camera would not contribute to the global-wide, network-wide performance unless we manually add it to the network. If a camera fails, it still works fine until the camera fails, because in this case, these 2 cameras would not know how to communicate with each other if we talk about static networks. If we change the position, there's also a problem. We can track quite nicely, but if we, for example, change the position, we might still be able to communicate, but if we define the communication, the direction of the communication, we might run into problems, right? And then finally, if we change the orientation, this is quite similar to removing a camera, of having a camera failing. Works fine as long as the camera is there, but if the orientation is changed, then we have a problem. We also tested this with our approach and compared it to such a static network. And I brought a video here. I hope this works. Yes. So what we can see here, this is the CamSim environment. We have these green dots representing our cameras, and we have these gray triangles, right? We have a black dot here, which represents an object. A triangle turning yellow means that it has an object within its own field of view. In this case, we have 2 cameras having the objects in its field of view, but only the first one is tracking it. This is indicated by this green line. All right, and on the right side, up here, we have time and utility, and this is accumulated over time, just to let you know. So what we also see here is after we trade, we generate this vision graph, right? And what will happen here in a few seconds is that this camera over here will be moved down here somewhere, and we will see how our approach is able to adapt to this change. We will see how the links will adapt, and old links will evaporate. So we added a couple of objects in here. They're just moving from left to right. And we already established quite a nice network for trading objects in a network. And now one of the cameras, now the camera moved, and we will see how these 2 start to evaporate and get thinner and thinner, and new links emerge in the network. We can continue tracking quite nicely. All right. We also did a comparative evaluation of this. This is an example where we added a new camera. We can see in the static approach, this new camera is obviously not included, while our approaches all include the new camera and can increase the tracking utility over time. This red line indicates where we have added the camera. This is a situation where we remove the camera. We can nicely see how the performance gain drops. while we are able to continue, track, and increase performance almost effortlessly after a failing camera. So this gives us a lot of flexibility and robustness to our network, right? So let's talk a bit about strategy selections. I said we have 6 different strategies: active broadcast, step and smooth; passive broadcast, passive step and smooth. But now the question is this really always the best way to set up all cameras with the same strategy? Well, if we use a simple performance measurement, trading off utility versus communication, and we look at this measurement for different scenarios, we find out that there is no dominant strategy, right, for these 3 scenarios. Well, for any scenarios, really. So we know that there is a clear trade-off between communication and tracking utility, right? And this trade-off allows an operator to select an appropriate strategy for his or her network, given his own or her own requirements. But as I said, until now, all our cameras operate the same strategy. So we're looking at what will happen if we enable our cameras to adopt different strategies from each other. Right? So what we found out, first of all, is that the location, the orientation, and the range is highly important for which strategy works best for our cameras. And we also realized that cameras in the same scenario might perform better if they have different strategies. So we started with a simple example. Just 2 cameras up here, right? Opposite directions. We filled them with objects and allowed them to track this. And if both cameras have the exact same strategy, then we only get 2 extremes, right? The passives and the actives. They don't care about the communication policy. But if we allow our cameras to adopt different strategies in the network from each other, so we assign heterogeneously, we get 2 more points on the Pareto front, right? 2 more options for an operator to select a strategy configuration. If we have more cameras, in this simple example, only 3, we get 216 different possible configurations with 216 different outcomes. If we have 7 cameras, we get a bit more than 278,000 possible configurations. All right? So we can see that it is beneficial to select a heterogeneous configuration for our networks. So we know location, orientation, and range of each camera is important for the strategy they use. But also we know cameras in the same scenarios might perform better. Well, the point is we actually can't do this, right? We can't define a priori which camera should select which strategy if we don't have a priori knowledge of the scene or the camera setup. So an operator would not be able to just select this one up here, right? Or one out of these ones. He might do this by just randomly picking one configuration, but he also might end up down here somewhere. So random is probably not the best idea. So we thought about how can we allow our cameras to learn which strategy works best for their current situation. And what we did is we looked at the multi-on Bandit framework, so machine learning approach. The multi-on Bandit framework is an idealized problem for encapsulating the explore versus exploit dilemma. What does it mean? Well, you can think of a gambler being in a casino and trying to decide which of the slot machines he wants to use, right? He's standing in a row of slot machines, and he knows that each slot machine will give him a random reward from a distribution he doesn't know about. But what he can do is he can pull arms and try to learn this distribution. Right? And then he can start to exploit good distributions that give him a lot of reward and avoid bad distributions for him. But that's something he needs to explore and then to exploit. All right? And the nice thing is, and that's very good for us, that this performance is measured online during runtime. Okay? So we implemented these Bandit solvers, and we took 3 from the books, namely UCB1, Epsilon Greedy, and Softmax, and implemented them on our cameras. So each camera individually runs one of these Bandit solvers. The thing is, we are measuring performance online, right, for each individual cameras. But we are still interested in the network-wide performance. So not the one of the individual camera. And we know that there is a strong codependency between the actions of one camera and the actions of another camera, and if they overlap. And also there is a complex relationship between local rewards and global system-wide performance. Right? So if we use this performance measurement I showed you earlier as a reward function for our Bandit solvers, the big question would be, is this enough? Does this work to achieve good global outcomes if we use a performance measure only locally? I'm going to take the answer right away. Yes, it is. Let's go back to a simple example. We know if we assign homogeneously, we only get 2 extremes. If we also assign heterogeneously, we get 2 more points on the Pareto front. But if we allow our cameras to explore its options and then also exploit its options, we get something like this. So we get better utility while reducing our communication. Right? And this is what we want to get to. Right? We want to get into this direction. So we tested this with all our scenarios. And what we got is, for all our scenarios, we always outperformed our homogeneous assignments. So with Bandit solvers, we were always better than just assigning the same strategy to all cameras. And in a lot of cases, we were even able to outperform our heterogeneous assignments. So an assignment we cannot select a priori. All right. So this is how we can use self-organization to select strategies for our cameras. So let's also talk a little bit about coverage and redundancy management. I think I have a few minutes left, right? Yeah. All right. So coverage and redundancy management. We want to do, again, have cameras operate together in order to track objects within a network of resource-constrained cameras. Okay? But for this work, and this is very recent work, we were looking at omnidirectional cameras. Right? So in this case, we have a 360-degree field of view. And we also want to do redundancy management and coverage. Right? So we were looking at cameras with zooming capabilities, so we can increase and decrease our field of view. For this work, we are just using active broadcast approach, so just the strategy of active broadcast. All right. So one of the big things here is the zooming capabilities. Why is this so important? Well, the quality of an image patch is highly dependent and determined not only by the image sensor, but also by the zoom of a camera. Right? So if we zoom in, we might get a smaller area covered, but we get it with a better quality in comparison to zooming out, where we might be able to observe a larger area, but the same patch has only lower quality. To give you an idea what I mean, here's a simple example. Right? This is a large image, a nice panorama of Mont Blanc. And to give you a clue what I try to get at, can anyone identify this woman in red here? Or at least give a slight indication where they think it is. Okay, no chance? I figure. I wouldn't have found it anyway. Give you a hint, it's up here, right? So let's zoom in a little bit. Where's the woman in red? Much easier now, right? So if we zoom in, we still have the exact same amount of pixels as with the large image, right? But now the patch itself has a better quality. So what we did now is we looked at how good does a simple detection algorithm perform if we change the resolution and the quality of an image. And we found a clear trade-off between the size of the image in terms of pixels and the confidence this tracker was able to detect a certain object. Okay. In general, for each camera, we get a local trade-off now, right? On the one hand, the image quality, which also relates to the tracking confidence. Then the area that is covered by the camera. And as we have just seen, the number of visible persons or objects, right? So we have a three-dimensional space we want to explore. But also, if we have moving objects and we have zooming capabilities, the complexity also increases quite a lot. And again, the network-wide performance is, again here, highly dependent on the actions of the other cameras. So in this case, it's not the strategy they are using, but in this case, it's the zooms they are using, okay? So we tested this, again, in our simulation tool, this time with omnidirectional cameras. So now no triangles anymore, but circles. And we were looking on a network-wide level, on the one hand for confidence again, so how much utility can we generate basically. We were looking at overlap. So what is the geometric overlap between circles, right? Between the fields of view. On a global evaluation, we can easily do this, right? And finally, we were looking at proportion. So proportion is a measurement defining the ratio between the tracked objects and the owned objects, right? So a camera might be able to own an object even though the object is outside its field of view. Then it's not able to track it. And we tested different zooming levels to identify how this trades off. Right? Obviously, zooming would be a continuous value. We discretized this and only defined 6 different zoom levels, right, to make it simpler for us. Okay, let's start with the first simple scenario. Again, green dots represent cameras. Circles here in black-ish represent the field of view. The blue line just indicates the boundary of the simulation environment. And what we get is something like this. I'm sorry, this is a bit small. Nevertheless, what we can see here is there is a clear trade-off between the overlap and the confidence we are able to achieve. There is also a trade-off between the proportion of objects being tracked and the confidence generated by these objects for the entire network. And there is a trade-off between the proportion and the overlap. I color-coded this. So what we can see, each point is represented in a 3-dimensional space, right? And the confidence is represented as the ratio of red in each point. Proportion is represented of the ratio of green for each point, the color green, and overlap for the ratio of blue. Okay? And we tried this also, again, with all our examples and always got quite similar results. Also large examples, very similar results, right? But these are, again, heterogeneous assignments of zoom levels. similar as we've done it with heterogeneous assignment of strategies. So we want also ask the questions, how can we enable cameras to organize their zooms, right, to achieve network-wide outcomes? And again, we don't want to use any a priori information, and we also don't want to add any additional information about the location of the cameras or their current zoom levels. Okay? And obviously, we also turned again towards Bandit solvers. So how can we use Bandit solvers if we only use local information? And the global version was confidence, proportion, and overlap. Right? The thing is, for local information, we can easily use confidence. Each camera itself, at each time, knows how well it is able to see an object. Each camera can define its own proportion. It knows how many objects it owns and how many objects it is currently tracking actively. But overlap is a bit of a problem. On the global scale, we were allowed to just use the geometric overlap, right? But on a local scale, if we have no information about the zoom level of another camera and no information about its location, we are having a bit of a problem. But what we can do is we can again exploit our trading behavior. Right? So let's assume we have here this person we would like to track. Right? And every time this person moves and this camera tries to initiate an auction, it will either get a response or not. Right? And if it gets a response, we know that there is another camera also seeing the object. If we don't get a response, the other camera is not seeing the object. And if it's outside, we can't do much anyway. But then another camera might again see the object, and this would indicate that we are not seeing the object, but another one does. So we defined these three different points as private points, where only we can see the object, as shared points, where the object is visible to ourselves as well as to another camera, or at least one other camera, and then others, where we are able to not see it, we're not able to see it, but another camera is able to see the object. And this information allows us to get an idea about our overlap with other cameras, right? We can use the ratio between the number of shared points and the total points. Right? This allows us to have an idea on how much overlap we have with other cameras at a certain zoom level. All right, so we now can use local information for confidence, proportion, and overlap, right? So we are able to measure our performance locally on each camera during runtime. The thing is, the optimal solution for the network is, again, highly affected on, and really a lot affected on the zooms of the individual cameras in the network. Right? So we have a strong codependency here. Now we defined a local reward function, including confidence, proportion, overlap, and we included 3 handles to trade them off in our Bandit solvers. And what we get here is, when we look at the proportion, the overlap against confidence and proportion versus confidence, as well as overlap versus proportion, this is what happens if we use our Bandit solvers. Right? We again are able to get results which are feasible within our space that we can explore in general. Interestingly, if we use our Bandit solvers, we can even explore spaces that we could not have reached without them. So with a static approach, we would not be able to reach these areas. All right. So what we also found out here is that proportion and confidence are very important for our tracking performance in the network. On the other hand, the overlap is very important for the resilience of the network, right? In case we have failing cameras. So when we use a focus on overlap, we're able to recover faster than when not focusing on overlap. So we tried to measure this over time. We defined a performance measurement for this special case for using confidence and proportion. And then we ran a scenario for 2,000 time steps, and after 1,000 time steps, we just removed cameras, right? And then our performance obviously dropped. The nice thing is we can see that this one up here performs quite well. This is the one that focuses on proportion and confidence equally. So basically the performance measurement we are doing, right? But after the drop, this green line performs best. And that's the one that focuses on overlap. That's because it creates the best resilience in the network. Okay? Well, let me get to the end of my presentation and conclude what we've heard in the last hour. I presented you a market-based approach to efficiently assign tracking responsibilities in a network of cameras. I showed you how we can use a socioeconomic approach to learn our neighborhood relations and how we can use them to deal with uncertainties and dynamics in the network. I showed you that when we use heterogeneous assignments of strategies in the network, we can outperform homogeneous assignments. But also told you that we would require a priori knowledge about this. Right. Then I presented you an approach where we used multi-armed bandit solvers in order to allow our cameras to learn the best strategy during runtime. And I presented you that we are able to outperform our homogeneous assignments when we learn our strategies during runtime. I also presented you an approach on how to self-organize our assumes for distributed redundancy management. And I showed you how we can use the handle on overlap for better resilience in case of failing cameras. All right. There's also quite a lot of future work that is possible. On the one hand, our bidding process currently does not include resource information, so we are mainly focusing on utility right now. That's the one thing. And then there are also a lot of opportunities when we include learning the movement patterns over time on individual cameras. Right. All right, this brings me to the end. I also included a couple of selected publications here, basically the work that this presentation is based on. And this concludes my presentation. Thanks a lot. I'm sure you have a lot of questions.